Yep. So I'm going to be dealing today with RL and RC circuits, which means resistors and capacitors only, resistors and inductors only. Then I will expand to that and put all three, capacitors, resistors, and inductor, that's RLC. And to make it easy on us, instead of going through differential equation trying to derive the solution to them, I made this sheet for us. If you have a differential equation that looks like this, your answer is going to look like that. And the question is, you just need to know what x sub 0 is equal to. And alpha is right there. If you have a differential equation that looks like this, x as a function of time will be a over alpha plus some constant, k. We need to know what that k is. And we go through it. When we get to RLC circuit, this is the RLC right here. So if you have a second order differential equation that looks like this, you could have one of three possible answers. It depends on alpha and w. Notice this is 2 alpha, that's w squared. If alpha is larger than w, your answer is going to look like this. If alpha equals w, is going to look like this. If alpha is less than w, is going to look like this. This is known as overdamped when we look at it later, critically damped, and underdamped function. But that's your RLC circuit. So hopefully you have that sheet. You can, if you lose it, I'll put a copy of this on our website, and you can actually have access to it all the time. Normally we go through the math and derive that. I'll let the math people do that. I don't have time for it. So let's take an example and see how we're going to use them. Let's assume we have this problem. Leave a space on the left. There's more stuff is going to be on the left side and the right side. 24 volts. And now I'm going to put a switch here. I have a 40 ohm resistor. I'll put the switch shortly. I have a 10 ohm. And I have an inductor. This is an RL circuit. It has resistors and inductors only. 5 Henry. And the question is, what is I sub L? And there's a switch here. That switch swings open at t equals to 0. Vivid, there's a copy for you. Oh, thank you. And to solve these, you always want to look at the circuit for t less than 0 and t greater than 0. When you have an inductor in the circuit, remember that what? V equals L di dt. I equals what? 1 over L, the integral of what? V dt. This is what we know about from negative infinity to t. This is what the current through the inductor. This is what the voltage across the inductor. And this equation also tells me what? That the current does not change in 0 time. So the current through the inductor is 0 minus should be the same as the current through the inductor is 0 plus. Or T0 minus T0 plus. I just use 0. So these are the three things I need to remember. So let's look at the circuit for t less than 0. The way the circuit is drawn, that switch was connected here. And I'm assuming this circuit been sitting here for a while, an hour, 20 minutes, but it's been there for a while usually more than a few seconds. Now here's the circuit. We have an inductor. We have a DC source. What did we say about the inductor? How does it behave when you have a DC source?
Linear element, 0 something, or whatever.
To a DC source, the inductor is going to behave as an open circuit. Short circuit, not an open circuit. Capacitor is an open circuit. Short circuit. So that means my inductor here is going to look like a wire attached there. And that should allow me to look at the circuit and calculate this current going through the inductor when t is less than 0. Just say I as a function of time for t less than 0. And what's that current? Isn't that the same current going through the 10 ohm resistor? So if you look at that circuit, if you redraw that circuit, you have 40, 24, and 10. And I'm looking for that current. I can use Ohm's law. What's I sub L equal to? The voltage is 24 divided by the resistor, which is 10. That's what? 2.4. So when you connect the circuit for a few seconds, that current, or millisecond, that current is not 2.4. If you let it sit for a few seconds, that current will be fixed value, constant value of 2.4 going through the circuit the whole time. And it will stay like that all the way for till you come up, before you open that switch, as 0 minus, or T0 minus, that's 2.4. I'm using the time the switch opens, that's time equals 0. So up to that time, that current going through that is 2.4 amps, going down. Now what's going to happen when T is greater than 0? The switch opens, which means that source is dangling. Right there, it's not connected. So for T greater than 0, what is my circuit going to look like? It's going to be 4. This is open. It's not even connected. That's what my circuit looks like. Oh, sorry, I missed the resistor on the top. Thank you. The 10. That source is useless. I can take it out. That's on my circuit. Now, I said one thing here on this page. I'm going to go back and take a peek at it. We calculated the current at 0 minus is 2.4. At 0 plus, this statement says the current's not going to change in 0 time, because the derivative here says there's no way that current can change in 0 time. So when you actually disconnect that source, the current through that at 0 plus is going to be the same as 0 minus for a few milliseconds. So the current coming through this at 0 plus, it's also going to be 2.4. So this really is going to react as a source. That inductor becomes my source, pushing the current down through it. There is no other source. It doesn't last long. Then the values start to decrease, then finally goes to 0, and there's nothing going through the circuit. So if I do a KVL equation right here, the only current going through the circuit is actually the current through the inductor. That's the only current. So let's use KVL here. What's the voltage here? Now, initially notice the source was right there. It was marking this plus to minus, right? So I can just write that. I don't really care what the value initially I'm looking at for t greater than 0. This will be 40 times I sub L plus the voltage drop right here, which is what? 10 I sub L plus the voltage drop here. What's the voltage? Where's my cheat sheet? The voltage is L di dt. What was L? I forgot to write it here. Was it 5 Henry? So 5 dIL dt. All of that is equal to what? 0. Let's clean that equation a little bit. 5 dIL dt plus 50 I sub L is equal to 0. Divide by 5. And now let's compare it to my equations, the ones I gave you. Does that look like the first one? Yes. Now people know where the video is coming from. They keep saying, where are you?
Oh, you could have stolen it from some online.
No, what's true?
Well, I'm not.
Yeah.
But then again, your name's on it too.
Yeah. I made these. So notice when you match these equations,
Didn't you already show it though?
yeah, it's all right. I just need to, I don't want it cutting, like I need the space. I didn't take it because of the name.
Oh.
I just want the space here. Notice that matches this form, doesn't it? We have a derivative, plus we use x here, I'm using I. My alpha, when you compare them, what's my alpha to that equation when you compare it? Alpha equals to 10, right? So the solution to that is going to be I sub L as a function of time, some constant, I'll use k, and I'll show you why I use x sub 0 here, some constant e to the minus alpha t. We know alpha is 10. My solution is going to be what? Some constant e to the minus 10t. And the question now, what is k equal to? How do you find what k is equal to? To find k, wait a minute, we know what the current through that is 0 plus, 2.4. So let t be 0 and plug it in. I sub 0 plus, that means t is 0, is equal to 2.4, which equal to what? K times e to the power of negative 10 times 0. What's e to the 0? 1 times k is k. K equals what? 2.4. So what is the current through the inductor at any given time? It's k e to the power, k, we know what k is. 2.4, right? E to the power of negative 10t. That's for t greater than 0. And let's see what that picture looks like. The graph of it. Let me write that equation on a clean sheet of paper. So the current through the inductor, we said for t less than 0 was 2.4. For t greater than 0, it was what? 2.4 e to the negative 10t. I did it for t less than 0 on the previous page, and it showed me the current is going to be 2.4. After that, it has this function to it.
Wait, and for like in the end, when you wrote I in parentheses 0 plus equals 2.4,
Yep.
it should be a 0 minus.
Nope, because 0 plus is the same as 0 minus. Right? The current as 0 minus will be the same as the current as 0 plus. That's why, because this equation tells you right there when you look at this, that current does not change in 0 time. If it does, you have an infinite voltage. So the current at t minus is the same as t plus. So taking advantage of that. So when you graph now what your current looks like, it's going to look like this. It's 2.4. That's the 2.4 here. That's the current through the inductor. And what happens after that? Decrease like this. And it levels off. Now technically, mathematically, this will never be 0. But let's say to go to 0.01. How long would it take that current? So we're not looking at a long time. We're just looking at a short period of time. How long for that current to reach, for example, let's say I want 0.1 amp. So almost, let's say 0.01. How is that? Isn't that close to 0? So how long is going to be before there's no current going through that? 0.01 amp, that's 10 milliamps. Small current. Can we get with that value? Sure we can. 0.01 equals what? 2.4 e to the negative 10t. Divide both sides by 2.4. Where's my calculator here? Uh, 0.01 divided by 2.4. 0.0042 equals e to the negative 10t. How do we solve it for t? What do? Natural log of both sides. And the natural log of e to any power is just the power. To solve for t, you divide by negative 10. Let me take the natural log of that number, ln of that number, divided by negative 10. It's going to take 0.55 seconds. So we're not talking about a large time there. We're talking about sometimes a second, 2 seconds, or even less than that before that inductor is no longer acting as the source. But right now that inductor is going to push the current through it. It's going to take about a second before everything is gone. After that, it goes back to 0. There's no current going through that. But we're interested in that time. Remember, we're talking in digital logic about changing from 0 to 1, 1 to 0. It has that form. And we like to shrink that time as much as possible. 0.55 is actually a big time. Nobody wants to wait half a second for something to happen. We want it the microseconds, milliseconds. So we constantly try to improve on the design to shrink it and shrink it and shrink it to make it drop much faster or rise much quicker. Let's try another one. Now, if I stay with this problem just to continue more before I leave it, actually, what about if I'm asking for the power? The power through that inductor. Isn't power equals V times I, or V squared over R, or I squared times R? So let's take a different problem. Just, I want to talk, well, yeah, I'll take a different one. I got bored with that one. I'll do a similar one to it. Let's put a voltage source here, 5 volts. If you know me, it doesn't take much. I get bored quickly. And I'm also stubborn. That's 2 things bad about me. Very stubborn. And I get bored. So if I look at a problem once, I go, oh, I had enough with it. It's similar, just put different numbers. I'll use the same inductor, 5 Henry. And my switch again, T equals to 0 opens. I want you to see it again. Sometimes you miss it when you see it once. So what is the process? So what do? Here's the process. We're going to do what? Look at the circuit when T is less than 0 and find what when you have an inductor? I sub L at 0 minus. That's what we need to do. That's the first step. Which will be what? I sub L as 0 plus. Then we're going to look at the circuit for T greater than 0 and write a first order differential equation. First order means you only have one derivative, not second derivative. Differential equation, dE. Write a first order differential equation, an equation that has first derivative in it. Number 3, look at the handout, this handout, because if it looks like this, your answer is going to be this. If it looks like this, your answer is going to be that.
You're giving this on the test.
Yep. Decide what the solution is. Decide what the solution is. Which one of them? Is it the top or the bottom? And the last step is really because I should have put a k here instead of x sub 0, but it's always going to be the value at 0 here. You saw me derive that. That turned out to be the current as 0, but sometimes I put k here. So solve for that unknown, which is x sub 0 or k. If it's like this one, this value is going to be whatever the current as 0. So you can bypass that. But if it's like this, you got to do what we did a few minutes ago. So the last step is solve for k.
And what is A?
Alpha.
Or no, the.
A, if this is a number, constant here.
That's just. Okay.
Just not if you have a constant, where this one, this actually the circuit I'm giving you, once t is greater than 0, has no source, called source free. And if it doesn't have a source, you will never have a number here. But what happens if I have a source after that? There's like a 5 volts here. So then you'll have a number here. And when you have a source there, then what's the value? The equation becomes like that. I'll give you one shortly. So this one is going to be when t is greater than 0, that source is gone. So let's follow these steps again. Let's look at the circuit for t less than 0. My circuit is right there. There's the 6. There's the 4. And again, that inductor has been sitting there for a while. It's going to react like a short circuit because you have a DC source. Notice that's a 5 volt. And what is the current I through the inductor? If I do a KVL here, oh, for t less than 0, I'm sorry, yep, the source was in. This is not a source free. I'm like thinking about the next example before I finish this. Better focus like a receiver trying to run with the ball before they catch it. So that source was there. For t less than 0. So obviously the current through that is the current through the 4 ohm resistor. So I sub L as 0 minus is going to be Ohm's law, which is the voltage 5 divided by the resistor, which is 4. That's 1.25 amps. And what's I sub L as 0 plus? It's going to be the same as I sub L as 0 minus. So it's still going to be 1.25 amp. So this is for t less than 0. For t greater than 0, the switch actually opens now. If the switch opens, what will happen? That source is gone. So my circuit will look like this. Now I know you're probably thinking, how come he didn't make the inductor a short circuit? I can't, because you just saw in that picture for a second or half a second, that's not gone. It's acting as a source. So I can't just erase it and put a wire there. After a while, I can erase this. Oh, okay, it's gone. But not during that time. So I gotta leave it there. And for this is write the differential equation, first order differential equation. Well, let's do that. Let's assign the current here in the same direction. That's I here. So 6I plus 4I plus L, which is 5 di dt, is equal to 0. If you add these two, that's 10 divided by 5, that's 2. Notice this is your alpha. That's your alpha. When you compare it to this equation, to that one, that's alpha. That's 0. I got to use the top equation. So my solution is going to be the current, the initial value, e to the negative alpha t. What's the initial value of the current at t equals 0 plus? You know what? I'll use k.
What did you do for the math from previous?
Added these two, that's 10, and divide by 5 to make that a 1. Do you see it? 6 and 4, 10I plus 5 di dt equals 0.
Why is there another DIDT?
Oh, that's I, I'm sorry. I wasn't looking right there. I gotta slow down. I. Yep. How many of these?
Yeah.
I think that's my second one the whole semester. Yeah. Having said that, I'll probably go through 4 of them this week. Yeah. We have a big party. I'm excited about it today. Eating party, so. Math department. Spanish food. So now, I need to find what k is. I'm going to prove to you is actually that number. That's why sometimes I just go and put 1.25, but I'll leave it as k. So the current at 0 is 1.25 is equal to what? K times e to the power of negative 2 times 0. E to the 0 is 1, 1 times k is k. So what is the current as a function of time? For t greater, well, I do it both. For t less than 0, it's 1.25 constant. For t greater than 0 is what? Or equal to it? It's 1.25 e to the power of negative 2t.
So this one's greater than or equal to 0, and the last one was less than or equal to 0.
It really doesn't matter because it doesn't change in 0 time. Right? So at 0, you can put the equal here or here. Will make a difference. Because we said the current does not change in 0 time. So at 0 minus is going to be 0 plus. You plug into this one or that one mathematically. When t is 0, that's 1.25. So the equal sign can be here or can be here.
That's awesome.
You're going to find out that if you look for the energy, we can do the integration. Power is I squared times R, and the energy is the integral of that. But the amount of energy stored in that inductor, the energy stored is going to be, what was the energy? Is it 1/2 Li squared? Well, which I? It's really the initial value. That's how much energy was stored in that inductor once that switch was open. Is whatever the initial current through it. In this case, my initial current was what? Remember, power, it's V times I, or I squared times R. And energy is the integral of power, dt. We can derive that. You're going to find out that the energy stored in that inductor was 1/2 Li squared. So that's why inductor called energy storage element. They have a lot of energy in them. Once that source is gone, they react or start behaving as a source there, pushing the current through it. And that's how much energy in it. 1/2 L times the initial value. So in this example, my initial current was 1.25. How much energy was in that inductor? It's 1/2 times the value of L times the 1.25 squared. And 3.9 joules here. Now let's see if I can take a capacitor instead of inductor. And I'll do source free first, and I'll make them with the source after that. So I'm trying to do source-free RL and RC circuits. That's really what I'm doing. There's no source once the switch opens. In a few minutes, I'll stop putting sources there. Let's say we have this circuit. 2 ohms here. Again, the same story here. I'll have a 9-volt source. I'm getting bored again of the same look, but I'll switch shortly. This is at t equals to 0 is going to switch. It's going to open the switch. And this is 4. And we have 10 microfarad. Now let's say I want to find the voltage right here. What's the voltage across the capacitor? Let's refresh your memory with capacitors. Again, this is what we did with the inductors. Capacitors. I, that's a C. I sub C equals I what? C dV dt. Which means the voltage across the capacitor is equal to what? 1 over C, the integral of I dt. What else we know? For a capacitor, the derivative, the voltage cannot change in zero time. So VC 0 minus has to be what? VC 0 plus. And to DC, now again, let's think about this. If you have a constant value, what's the derivative of any constant? 0. That means the current is 0. For the current to be 0 is going to behave as what? Open circuit. And to solve a circuit that has capacitor in it, we're going to do the same thing as the inductor, which means what? Step number 1, we're going to look at the circuit. For t less than 0, but instead of finding the voltage as 0, I already gave you a hint. Instead of finding the current as 0 minus, what are we going to find? The voltage as 0 minus. And that's going to equal the voltage as 0 plus. Then we're going to look at the circuit. At t greater than 0 and write a first order differential equation. Decide on the solution from the handout. When I say decide, meaning am I going to use this one or this one? And that will depend, do I have this is 0 or do you have a number here? If you have a 0 there, you're going to use that one. If you have a number, you're going to use this one. And the last step is find K. I should have recalled this K instead of X sub 0. It's always going to be X sub 0, but I'd rather use K there than I could have been K for both. You know. I didn't think it through completely. So these are the steps I'm going to use. Well, let's take the first one. Let's look at the circuit for t less than 0. T less than 0, the source was connected and this is going to work as an open circuit. And what is the voltage right here? This is 0 minus. So I'm looking at the circuit for t less than 0. Can you tell me what that voltage is? Okay. What is, if this is ground, what's this voltage here? 9, good. Let's calculate the voltage right here. What's the voltage drop across the 4 ohm resistor here?
9 minus VC.
No, just the voltage here. Ohm's law. What's the drop? Isn't voltage equals R times I?
Yeah.
What is I? 0. It's an open. 0 times 4? 0. That says this end is going to be 0 volts lower than that end. So that's a 9 volts. So what's VC 0 minus? Is equal to 9, which also equals VC 0 plus. I could have just took that resistor out. I just I could have took my white out and erased that 4 ohm resistor and said, what's the voltage right there? That's in parallel with this. 9 volts. Part A is done, or the first step. Look at the circuit for t less than 0. Calculate the voltage at C equals 0 minus, which equals 0 plus. Second, we look at the circuit for t greater than 0. Now that source is gone, so my circuit will look like this. And I'm looking for the voltage here. Most circuit books, they make you memorize things. I don't like to memorize things. You know, I don't have to tell you, I don't even open the book when I leave the room. So it's in the drawer. You see me opening the drawer and opening. So if I memorize these, I will never remember them by now. I'm old. I can't remember the stuff. But if you know how to do them, you can look at them 10 years from now. So, there's the process. So, well, I can do KVL here. But that will give me the current through the capacitor, not the voltage. Okay, let's see. Let's go through that. KVL and through this one we have what? 2I, or I sub C, plus 4I sub C. And wait. What is the current, the voltage across the capacitor? 1 over C, the integral of I dt. Not what I was hoping to get. Where's my handout? I don't have any equation that has integral in it.
Just do the derivative.
Ooh, very good. What's 2 and 4? He was hesitant, like, do I do a derivative? What is 1 over 10 micros? Do the math. 1 divided by 10 micro. Is that 100,000? Or 10 to the 5th? Okay. To get rid of the integral, you learn that in differential equation, is you take the derivative. If you take the derivative, this becomes what? 6 DIC dt plus 100,000 I sub C equals to 0. The integral is called what? The antiderivative or antiderivative. It's the inverse of the derivative. The inverse of a function, they cancel each other out. If you remember from math, we used to tell you to prove that the function, the inverse, those are the inverse of each other. If you do this one, the result is always x. Or if you take the inverse of the function, you end up with the x, whatever x is. So if you take the derivative of the integral, they cancel each other out. You end up with that expression, which is I. So now divide by 6. So I have di dt, or I sub c dt, plus what? 16,667 roughly. I'll just round it. Does that match this equation now? The top one?
Yes, sir.
What's my alpha? 16.67. So the current through the inductor now, the capacitor, the current through the capacitor is equal to some constant K e to the power of negative 16,667 I sub C. Oh, not I sub C, times T. God, I gotta go home. Well, who cares? I'm not looking for the current. I'm looking for the voltage. The question, what's the voltage across the capacitor? What do I care if you give me the current? It's like me saying, solve this problem. You go, tomorrow's Friday. Big deal. That doesn't help me solve that. Well, can I solve now for this one? If you know the current through that capacitor, can you find the voltage? What is V equal to? Well, according to this equation, V equals what? 1 over C, the integral of that I dt. We all took calculus. I'm hoping you all did take calculus. So the voltage across the capacitor now, it's 1 over C, the integral from negative infinity to t, I sub c dt, or 1 over c, the integral from 0 to t, I sub c of dt, I sub c t dt, plus the voltage across the capacitor is 0 minus. So let's integrate that. What is C equal to? Ten micro? 1 over 10 micro. The integral from 0 to t. And what was the current? We just solved for the current. Where did I put it? Oh, right here. K e to the negative 16,667t dt plus the initial velocity as 0 minus, which is whatever it was. You know what? I'll leave it from a negative infinity, actually. Why even break it down? Go from negative infinity to t. This is negative infinity to 0. No, to t, which can be broken down if you want from 0 to t plus the value at 0.
9 volts.
Huh?
It's just going to be 9 volts.
Well, let's see. How do you integrate this? You're going to take k in the front over 10 micro. What's the integral of e to the minus 16,000?
It's e to the minus 16.
Isn't that 1 over negative 16,667 e to the power of negative 16,667 t, as t goes from where? Negative infinity to t.
You don't want to put in 9 for K?
Well, I'm going to do that later.
Oh, okay.
Upper value minus the lower value. Now, if you plug in minus infinity for t, this number becomes massive. That's the problem, so maybe I should break it down to a 0. K over, oh, the math is ugly now. That's why sometimes they make you memorize them. Go, oh, just remember this. and go from 0 to t, then add to it VC at 0.
Yeah, how you doing? I get it.
Uh-oh, he's happy, Bernsey. Now, you can plug in the limits, go through it, and solve it.
Great. There you go.
What is he, a greeter today? Minus, when it's 0, e to the 0, that's 1, right? And you solve it. And what you're going to find out that k, really that value, happens to be VC as 0 plus or 0 minus is equal to k. So if you wanted to avoid that a while ago, you could have put the 9 volt here, and that would have been your answer. I just want to take you through the math and show you why sometimes they make you memorize that and put that initial condition so you don't have to kill yourself and go through this math.
So this is only for the case we don't have an uppercase A value, right? Or like the
Yep.
second. Right, this
We're going to do the same thing actually when I have a source. I'm going to do the next example where you're going to have a number there.
Right, so, but it doesn't work for that, right?
It'll be different. It will not be, but you're still going to use that number, but it will not be that number. That's why I don't want to call it x sub 0, because it will not be. This k will not be. It might, in some cases, it might be, but it's not always. So that's why we call it k here. The question here, we know it's going to be the initial value. Can we assume this is going to be the initial value? The answer is no. This one, yes. This one, no.
Can you move that paper over?
It's like he's like creeping by.
He's getting closer. Okay.
He's like right there.
He's loud.
Now let's put a source there. And you know what? Ooh, let's have fun. Let's put more than one inductor. Remember what we did with them. Make the circuit more complicated. But still RL, RC circuits. I'll do one of each. How much time? I might be able to sneak one of each.
Good.
And this is 1 millihenry here. This is 50 ohm. Oh, let's put another inductor here.
I'm calling an op amp.
2 millihenry. Oh, we could. Let's put another inductor here. 3 millihenry. Nope, that's next class.
Yeah, once it's
You're only going to see this class, you'll see resistors and inductors, resistors and capacitors, RL or RC. You will not see a combination. That's next class.
So capacitors, inductors, and resistors, those are known as linear elements, right?
Yes.
So what are nonlinear elements? Like
Transistors.
semiconductors?
To take transistors.
Transistors?
Yep.
What about semiconductors like diodes? Are those also nonlinear?
If you look at the diode, actually, what do you know about diodes? How'd you know them?
Mr. I went to pass.
There was that one homework.
Yeah, the Xeno diode for the homework. That was snuck in.
I know.
That's a different story. Yeah.
Alright.
So now, look at that circuit. At t equals 0 is going to open. So for t less than 0, the thing was closed. And if I actually redraw that nicely, remember, I forgot to tell you what I'm looking for. Let's say I'm looking for this current, Isabel. Now you know these two inductors in parallel, we can find the equivalent of them, product over the sum, if I want to. And it will not change that current. So if you want to make life easy on you, you can say, well, let me minimize that circuit before I start shorting things and adding things. And the 120 and the 60, big deal. Why do they have two resistors? Why not just make one? That's 180. That's 90. 1 millihenry. And we got what, 50? And I can take these two, make another inductor. And what's 2 times 3? 6 divided by 5? Is that 1.2 Henry? Millihenry? 6 over 5? 1.2, I think. And if I'm looking for that current, combining these two resistors, does it change that current? Combining these two inductors, does it change that current? No. Combining these two inductors, does it change that current? No. So I can even simplify it one more time to make it less ugly. This is t equals to 0. $180. And I can make it one inductor now of what? 2.2 millihenry and 50 ohm. Which one you put on the top, the 50 ohm resistor, the Henry down, doesn't really matter. And now I'm looking for that inductor. So I didn't even discuss any of the stuff yet. I'm just saying it's too ugly of a circuit, too many things in it. Let's make it a little bit cleaner. So for t less than 0, that switch was closed. So that's what my circuit looks like. Now when you look at this resistor, the 180, it's attached right here. What is the relationship of the 180 to the 90?
180 to 90?
Yep.
They're parallel.
Are you sure? The answer is yes. Just making sure. I'm waiting for him to see. Yeah.
I don't know, like it looks in here, like it's.
Notice the top is attached here, the bottom is attached here. They are in parallel. Just because I'm asking that doesn't mean you're wrong. I just want to make sure to tell me why you think. Oh no, that's not a compliment. Wait a minute, this is on video. Never mind.
There's nothing wrong with it. It's just it puts doubt into your mind. That's all.
That's what my circuit looks like. And I'm looking for this current. I didn't even start looking for t less than 0, or greater than 0. I didn't even discuss it yet. I'm still enjoying this problem, simplifying it, shrinking it. And I'll start looking in a few minutes. This is actually for t less than 0. I'm looking at it. Because for t greater than 0, that source is open. It's gone. So I'm still for t less than 0 here. These two in parallel, the product over the sum. Where's Bernie to say good morning to her? Burns, come back.
I told him I put the wrong video. I don't think he cares.
So this is 18. The two resistors combined will be 60. Hey, let's think about something called source transformation while we at it.
Can you do source transformation with the inductor?
Says as long as you got this.
Oh,
I think he's asking, like, can you
Um,
do it with, like, other than elements?
Well, we might. We gotta wait till next semester. Can't give you everything this week.
We're like,
do it now.
we can't wait to find out.
Actually, the answer is yes.
to be continued, right?
Yep. So it's source transformation here. And notice, since we have a DC source, what will happen to that inductor? Short circuit, right? Now let me start thinking about that. 18 times 60. I mean, I equals V over R. So that's 18 over 60. I think I might have said time instead of over. 18 divided by 60. Oh, wait a minute, that's in parallel, right? Oh, can't do source transformation. Today is one of the days I should. Those medications not doing me any good. I almost took yesterday off. I was like dying. I took some nice pills. Everything is wonderful today. I can't really do source transformation because they are in parallel. They have the same voltage. That's a voltage source. You can only do source transformation if it's a voltage source with the resistor in series or a current source with the resistor in parallel. So I can look at that and I say, well, the voltage here is 80. So this actually looks like this. This is a short circuit now. Can we find what that current I is? 18 over 50. So the current through the circuit is 0 minus equals, is that 0.36? Which is the current through the circuit at 0 plus.
So,
Yes.
use current to divide the right?
The three of them in parallel, right? They have the same voltage. Yep.
That's what you use, right?
I equals V over R. That's why I use Ohm's law.
Oh, you use Ohm's law.
This is 18 volts right here.
Parallel circuits, the voltage in the
18 divided by 50 is 0.36. Now let's look at the circuit for t greater than 0. I do feel like my head is going to pop. I don't know what I got. Oh, there comes the greeter. For t greater than 0, that source is going to open, which means this voltage source is gone. So what you have is 180 on the top, the 90 here, everything else stays, but the source is gone. So if I put that circuit here, so I don't have to redraw and simplify it, just disconnect the source here, you will have 180 ohm, 90 ohms, 2.2 millihenry. Oh, there's still source-free circuit, huh? Oh. Well, I was hoping to get a source after. Yep, I screw up, still source-free. But just a bigger circuit. This is 60. .2 millihenry. .50. Ohm's law, KVL, 60I, plus V, which is what? L di dt, plus 50I equals 0. 2.2 milli di dt, plus 110, I think, I equals 0. Divide by 2.2 milli. It says 50 on my calculator. I don't trust myself today. So if somebody want to verify that, you can. So guess what the equation is going to be? I, as a function of time, is going to be the initial value, e to the power of negative 50t. What was my initial value there? I forgot, it's been a while. What was it with that problem? 0.36? I, as a function of time, is 0.36 e to the negative 50t for t greater than 0. So this is also a source-free circuit. My plan was to put some sources there, and maybe I'll do that next class.
Wait, when you divide 110 divided by 2.2,
Milli.
you do 2.2 times 10 to the negative third?
I thought that's what I did. Maybe I'm wrong. I said I don't trust me. 110 divided by 2.2 e to the negative 3.
Yeah.
It's 50,000.
Yeah.
50K. I said, don't trust me with these. 50K, that's 50,000 T. Sounds like a cow.
That's kind of what I was going